Question 5.1 and 5.2. We are first asked to define reaction rate. This is the change in a quantity of a reactant or product, either concentration, moles, volume, mass, over the change in time. Next, we are given a reaction between carbon monoxide and oxygen to form carbon dioxide, and are told that these three gases are in a sealed container. We are given a graph which shows how the concentration of oxygen gas changes over time. We can see that at the start of the reaction, when time equals 0, the concentration of oxygen gas is at its highest. And over time it decreases as it is used up to form the product. Eventually its concentration levels off. Now, from the definition, one way to write the rate of the reaction is in terms of the concentration of oxygen gas. We could say that the rate of the reaction is equal to the change in concentration of oxygen over the change in time. We are asked to compare the rate of the reaction at 10 seconds and 30 seconds. Now the gradient or slope of a concentration time graph is the rate of the reaction. The change in y is the change in concentration of oxygen gas, and the change in x is the change in time. So if we find the gradient of a tangent to the curve at time equals 10 seconds, and the gradient of a tangent to the curve at time equals 30 seconds, we can compare the rates at these two times. We can see that at 10 seconds the gradient is steeper, and this indicates a faster reaction rate, while at 30 seconds the gradient is shallower, and this indicates a slower reaction rate. So the higher rate is at 10 seconds. This makes sense, as the reaction is faster nearer the beginning when there is more of each reactant, and so there are more effective collisions per second. Next, we are told that the reaction vessel is 3 decimeters cubed in volume, and we need to calculate the average rate of the reaction in the first 10 seconds in moles per second. The average rate in the first 10 seconds is found by taking a point at time equals 0 and a point at time equals 10 seconds, and then finding the gradient of a straight line between these 2 points. So we need to find the change in y over the change in x, which we said earlier is the change in the concentration of oxygen over the change in time. Reading off the graph, we can find the y and x value of each of those 2 points, and solving, we get 0.012 moles per decimeter cube per second. Now this is the rate at which oxygen gas is used up in moles per decimeter cubed per second. But we want the rate in moles per second, and not for oxygen but for carbon dioxide. Now there are various ways to do this problem. One way is to start by getting rid of the per decimeter cubed unit, by multiplying the rate of oxygen consumption by the volume of the vessel. We can cancel the decimeters cubed with the per decimeters cubed, and multiplying out we get the rate of oxygen consumption in moles per second. Now that we have the right unit, we need to get the rate for carbon dioxide production. From the balanced equation, we can see that 2 moles of carbon dioxide are produced when every 1 mole of oxygen gas reacts. And so this means that carbon dioxide is produced at double the rate that oxygen is used up. All that is left to do is to multiply the rate at which oxygen is used up by 2, and we get 0.072 moles per second. Again, this is the average rate of production of carbon dioxide in moles per second for the first 10 seconds. Next, we are asked to identify the reactant which is in excess, carbon monoxide or oxygen. We are not given any information about carbon monoxide. However, we do know that the concentration of oxygen becomes constant after some time and is not 0. So oxygen is not completely used up. Therefore, it must be in excess. Remember, if oxygen was the limiting reagent, it would all be used up. So carbon monoxide must be the limiting reagent. Lastly, we are asked what would happen to the initial gradient of the graph if the reaction vessel was smaller. Well, if the number of moles of each reactant put into the new vessel is the same as before, but the volume of the vessel has decreased, that is, the volume is smaller, then the concentration of each reactant increases. An increase in concentration causes a faster reaction rate as there are more frequent effective collisions.